Alright, what's going on, guys? So today we are going to be talking about a review of Yang-Mills theory. And so in Yang-Mills theory, we are going to be sort of generalizing the concept of Maxwell's theory, and when we do that, we're going to be seeing a few things that are lost, i.e. local invariance within gauge symmetries are lost. But then we're going to circle back to this idea of holonomy, which is something we've talked about in earlier videos on quantum gravity. So we're going to be doing this sort of full circle thing on talking about Yang-Mills theory. So this is probably going to be a long video, maybe, I'm guessing maybe 45 minutes, maybe even an hour, but hopefully not that long, because Yang-Mills theory is a very expansive theory. There's a lot to it, and to provide a review on it is it was sort of hard to piece this together and figure out what exactly I wanted to put in this and what I didn't. And I think what ended up happening is that it ended up being a little bit longer than I really wanted it to be, but it's more canonical in a sense that it covers more. So with that being said, make sure to hit that like and subscribe button. Make sure to go on to my Patreon page if you want to support the channel, get notes, get full videos. Again, this is just part of a video. You can also go ahead and become a member on the channel as well if you want to as well. So let's go ahead and get started. So in the last video, we gave a rundown on the canonical form of Maxwell's theory of electromagnetism. We're now going to move on to Yang-Mills theory before we circle back to the canonical form of quantum gravity. Okay, so at the core of Yang-Mills theory is this generalized Lie algebra valued gauge potential. And what we mean by that is that we can express the gauge potential A. This is sort of the thing that when you take the curl of this field, you get the magnetic field. When you take the gradient, you get the electric field. But we're going to expand that now. We're going to say, well, we can generate this thing in terms of, or we can write this thing in terms of this matrix here, right? So this matrix here is A, I, mu, transforming something called Ti. Now Ti is going to be called a generator in a Lie algebra. Okay, we haven't really gone over Lie algebras, but the idea here is that Ti in the SU2 case is going to be our probably spin matrices, or some sort of representation of SU2. Okay. The Pauli spin matrices are just the most common ones that you'll see. In the SU3 case, Ti will be the Gelman matrices, okay? So an I is going to run through 1, 2, all the way to n squared minus 1. So whatever SUN, right? So if we're talking about SUN, so SU3, then we're going to put 3 into here. It's going to be 9 minus 1 is 8. There's 8 of them. There's 8 generators, 8 Gelman matrices, if you will. So we're not going to go into the matrices, and so that'll be a separate video, right? So that's when it comes to physics, right? The SU matrix, the SUN or the SU2 matrices are going to be associated with spin. The SU3 are going to be associated with color charge. But again, that's sort of beyond the scope of Yang-Mills theory. Really, the point here is that we are expressing our potential in terms of these things. Okay, so we have our these guys here. Oh, I'm gonna make that thinner. These guys here, well, they can be Pauli spin or Pauli spin matrices. Or they can be the Gelman matrices. What these really are, though, are representations of a type of transformation, namely Lorentz transformation in a complex form. Okay, and they obey this Lie algebra, right? So they obey this Lie algebra. We're not going to derive this Lie algebra right now. We're just saying that at the core of Yang-Mills theory is fundamentally, at the core of Yang-Mills theory are these are different representations of the Lorentz algebra, essentially. So we could think of this newly defined gauge potential is now a matrix, right? Because it has two indices, I and mu. So we could think of this as a matrix. And in the SU2 example, where the generators are going to be the Pauli matrices, we can sort of look at this as, well, we have our potential. This is our EM potential, our 4 potential. That's written like this, which is what we just stipulated before. Well, these guys can be thought of a matrix. Here's our matrix, and this guy here, well, these can be our Pauli spin matrices, right? Where this one is just the identity. This one is our a Pauli spin matrix, right? So I always forget the form of each one, but we have entries where we have, I believe one of these is going to be 1, -1, 0, 0, and then we have like an I, negative I, without the embarrassment of potentially getting one of these wrong. I'm just going to say, well, okay, these are our spin matrices, and this is something that's going to transform this thing, right? This is some vector, can be thought of perhaps as some vector, not really in space-time, right? Because these, that's sort of a leap in logic there, but we could sort of just think of this maybe as a matrix that moves these generators, and when you move these generators, you get our gauge potential. But this is everything really just comes down to this equation right here. Okay. Notice that we've turned the gauge potential into a matrix. So the reason for this is because this is due to the fact that we can construct different representations of the Lorentz transformation. In the U1 representation, we had the normal A mu in the gauge potential. However, when it comes to SU2, we need a different representation for the same potential. The gauge potentials act as things that enforce local invariance in our Lagrangians. So again, we haven't really talked about how these things enforce local invariance in this playlist, but we have done that in other playlists, in our quantum field theory playlist. And we'll go over it again in future playlists and all that. But just because this is a rundown of Yang-Mills theory, I'm going to try to cut to the chase as best as I can without having this video go on like for hundreds of hours. In the U1 case, we're presented with this type of derivative. This is a covariant derivative. We have our normal partial derivative with the addition of this guy here, right? So here, this is where our gauge potential comes into play with our derivative. And our anti-symmetric EM matrix it looks like this, or not matrix, but a tensor, or electromagnetic field strength tensor looks like this. This thing, this is what I said before, this is what's at the core of Yang-Mills theory. On this side, this blue side here, we're dealing with A mu. On the red side here, we're dealing with this side of the equation, where we're actually dealing with these A I mu's. And so you might see this in textbooks where C, this will stand for, like, say, color charge or something like that in SU3 case. But in the SU2 case, we have this index that could run from 1 to 2, right? So in the Pauli spin matrices, it's going to run from 0 to 3, right? And then we have these guys here to sum over those. Okay. And then this guy here looks a little bit different also. We have this guy here, and then this part here, right? It looks kind of familiar to this. We have these structure constants, F, so those play a role in this tensor. But then we have these two other guys. We're not going to derive this right now. We just want to keep this in mind, and we'll derive it maybe later, maybe not, because again, this is just a review. Okay, but we're going to derive things in here, and the things we're going to derive are going to be a little bit more important. And so let's now start by talking about canonical analysis of the Yang-Mills action. we start off by proposing a Yang-Mills action and splitting it up into the 3 plus 1 form. Okay, so the 3 plus 1 form, if you're not aware, is going to be this form right here, right? So this is our Yang-Mills action, this is our EM action. However, we have this new I introduced. And what we're doing is we're splitting this up into the 3 plus 1 form, right? So this is the 3 part, right? Because this is the spatial part, and then the temporal parts are right here. But because of anti-symmetry, we can collect these two terms, and we get this 1/2 here, and we get this -1/4 here. Okay. And so this guy is going to be, this guy's going to be inside of this guy. So this thing here is part of our Yang-Mills action, as you can see right here. But then we subtract this thing, right? So this thing is still part of our Yang-Mills action. So we're just going to keep this one for right now, this part right here for right now. So we're going to say the Yang-Mills action is going to be equal, not equal, but is going to be related to this object here, right? Where we say, if we want to take a change in the Yang-Mills action, this is sort of like taking a derivative, and so we take the derivative of the outside. Again, this is just the chain rule. That's going to get rid of this 2, and then we have a change in the inside, right? Again, that's this guy. If we say this, then we can get to this point. Okay, so that's this right here. Okay, so this is kind of a derivation. And let's see how this is kind of a derivation of this thing, because if we say this, then we get to this. And then if we define the canonical momentum to be this guy here, which is this, right? Because the change in this with respect to a dot is just going to be the constant out here, which is this guy. And we identify this guy with our electric potential, our electric part. That is going to be equal to all this here because of this, right? So we're saying this is equal to this, but it's also equal to this. Okay. Now, it now follows that the Yang-Mills action is going to be this guy right here, right? So this is so these two guys minus this here. So this is our Hamiltonian and our Lagrangian. And if we just expand things out now, right? So this guy we said was equal to this, and then we have all this in here. We now color code everything to match everything up, and then we get this guy right here. So from here to here, we are taking, we're extracting this guy out of these two guys, right? So we have this guy here, and it's right here. Okay. And so we take that out, and we have this here now. This, we exchange the J, right? So we have the J and the I, we exchange that, these two guys. Okay, and then we have this guy here. So again, K and J, right? So we're just swapping things in the, this is like we're just renaming dummy indices. Okay, and then to get from here to here, well, we can see that this is just a derivative term of of our E vector, right? So, and then we have that extra I index. So we get to here. And notice the difference now between the Yang-Mills Hamiltonian and the Maxwell Hamiltonian. The Maxwell Hamiltonian is going to look, we've derived was this, where we have a partial derivative out here. But in the Yang-Mills case, we have this guy here, which is now a covariant derivative. Okay, and that's this guy right here. And so what we've done now is we've said, we've defined this guy, and we've defined this guy. And when we did that, we were able to show that our Yang-Mills theory is essentially the same as our Maxwell theory, with the exception that instead of a partial derivative, we get a covariant derivative out here. Okay, so this is almost like a derivation of this guy and this guy. It's just somewhat of a backwards derivation because we're saying we suppose these two things and we can get an expected outcome. Okay, so that must say something about the structure of the two things that we proposed. Okay. In Maxwell's theory, we defined a smeared Gaussian integral as a gauge generator, and we're going to do the same thing for Yang-Mills theory. So in Maxwell's theory, if you recall, we defined this thing to be our generator. This is the function that we place in our Poisson bracket to get us our gauge, our gauge transformation. And so we're doing the same thing in Yang-Mills theory, again with just the exception that instead of a partial derivative, we have our covariant derivative. Okay, and this guy is related to, I just wrote, this could also be our canonical momentum because we defined it here also. Right. So Yang-Mills theory and Maxwell's theory are so far pretty much the same thing. The only thing we're getting out of Yang-Mills theory that we don't get out of Maxwell's theory is that we're dealing with representations of the gauge potential as opposed to the gauge potential itself, and therefore the thing that's costing us is an extra part to a derivative, which is a covariant derivative, not just a partial derivative. And so we are now going to calculate the Poisson brackets for the canonical momenta with the gauge generators. But first, here's the punchline. I want to give you the punchline first because this can be quite daunting, what we're going to do next. We're going to derive a lot of this stuff, okay? We're going to derive these guys in particular. So before we get into deriving these relationships, it's worth noting that the electric field analog and the field strength tensor analog in Yang-Mills theory are not invariant quantities under gauge transformations and therefore are not physical observables in Yang-Mills theory. That is to say that you notice these things are zero, these things are not. When they're zero, we can say that the electric field and the magnetic field are observable quantities of that theory. Whereas in Yang-Mills theory, we say that if they're not zero, then they're not observables, okay? And this sort of goes into the idea of quantum mechanics and how we can understand what mathematically what's an observable and what's not. And so with that being said now, let's just continue this really quick. It's almost as if diving into the world of SU2 gauge transformations comes at a cost, okay? Namely losing local gauge symmetry. However, we do gain insight into some new invariant quantity, which is going to be the holonomy. And this is where things start, this is where we're going to start talking about loops and loop quantum gravity, okay? So this is really where loops, or the idea of loops and loop quantum gravity are going to come from. Okay, so let's continue. Alright, so we're going to start off with the gauge transformation of our gauge potential. Okay, and so our gauge potential is going to be this guy right here. So this guy right here, again, we're doing the same exact thing as we did last time with our Maxwell theory. So we take the Poisson bracket, we divide both sides by this E, right? And so, or not both sides, we're multiplying by 1, right? So we're multiplying by 1. We take it out, and we have our gauge transformation again was given to us with a covariant derivative, and then we can expand all this out to our covariant derivative on E. It looks like this, as we've seen before, and then from here to here we are just multiplying a few things out, right? So we're taking derivative of this guy here and multiplying by this. Well, we can swap we can make this negative and swap the derivative for this guy instead of this guy. And this is just by, we're doing, if you've seen this, we've done this already, but this is essentially integration by parts. Integration by parts. That's how we get from this guy to this guy. And then we have all this here, okay? Alright, so now we have this. So to go from here to here, we're just distributing this guy now. And then after distributing, we get this guy here, right? Because we want a Kronecker delta to collapse K and J. Right, so K and J, we want Kronecker delta to collapse C and B. So there's C and B, and we want a Kronecker delta to collapse the location from Z to Y. Okay, and we're doing the same thing here. We're using all these Kronecker deltas to collapse all these things, because we really only want the change in this to, with respect to this, to be 1 whenever all these are the same. And so when we do that, we're collapsing a lot of stuff, and we're able to get rid of this integral over Z, right? Because we're just collapsing down to Y. And here, so that's how we get from here to here. From here to here, we're swapping just our these indices, and we're making that negative because this is an epsilon tensor when we do that swap. And then we get this guy here, right? Because this guy here is really just the definition of the covariant derivative of our gauge transformation. So lo and behold, we get our expected gauge transformation of our 4 potential. All right. And so this guy here, let's see, how is that different from? I'm just plugging everything back in, right? So I plug this into here, and we get this, and so we get this after, right? So really what we're saying is that this thing is our gauge transformation, right? So this means that our gauge transformation of the gauge potential is this guy here. All right, let's do it for the canonical momenta, right? So that's our E. And you know, I'm going to actually, so you can actually pause the video here. You can, I put all the steps if you want to follow, but I'm not going to go through this step by step. Again, you can just pause the video, but you can see how we get to this point down here. This point down here gives us the gauge transformation. This means that our gauge transformation of the canonical momenta is this guy right here. All right. So just for the sake of the timeliness of this, because I don't want this to go on for too long, I really just do the same exact thing as I did up here, down here. All right. So and I make notes on the sides of how I get from one step to the next. All right. Now for the gauge transformation of the field strength tensor. To do this, we start with the Poisson bracket of the electric field tensor with the field strength tensor. Okay, so this is going to be a doozy. So let's go through this as best as we can. So this guy is going to go to 0 because this thing is not a function of this, and this guy's not a function of this guy. And so we're left with this, and so this guy, when we have this in mind, we can say that we have this, which is this guy, multiplied by this, which is our F is all of this, and then this is right here. Now we use Kronecker deltas to collapse things as we've been doing, and when we do that, we get this down here, and so now we're just taking derivatives, right? So derivative of this with respect to this, this with respect to this, and all this with respect to this. And so that's what we get down here. And I'm highlighting all the indices just so that you can keep track of them. Now to get from here to here, again, a bunch of Kronecker deltas, right? So we're collapsing I and J, collapsing A and C, we're collapsing X and Y, and we still have this derivative in here, but derivatives of Kronecker deltas, that's not really going to do much. We're going to keep the derivatives in here because we see we keep them in here for right now. But yeah, so just a lot of this is collapsing using Kronecker deltas. Same thing for this term, and then same thing here, right? We have Kronecker deltas, and so now we can multiply both sides, or not both sides, we're multiplying everything in the brackets here by this guy. And when we do that, here's our ij, here's our, let's see, ijk, so we have ilk, so we're changing L to J, right? So L and J, because we have an L right here and a J right there, right? So that's how we're changing these things with these Kronecker deltas. J right here. And so once we get from here to here, to get from here to here, right, we're taking it back out, but with different indices, with different index labels. And when we do that, we see this term right here, and so we can rewrite this now as a commutator over indices for each one of these. All right. Putting this on hold for just a moment, we now calculate the functional derivative with respect to E. The functional derivative with respect to E is going to be this guy right here, right? So the functional derivative of our generator, our generator function. And we're doing really just the exact same thing now, right? So we're so to go from here to here, right? So again, this is this here is the integration by parts. This here goes to this one here because of, let's see here, we have G, we have A's, we have E, and then we're really just distributing, right? So this is really just integration by parts. I don't even know why I put this in here. Maybe just to help us keep track of this, what this means. But then we do this, right? So this is all the same thing. We're distributing this back into the parentheses, collapsing things with our Kronecker deltas, and we get down to here because again we're integrating over W, and our integration measure is on Y now. And so we have everything in terms of Y because we're driving everything to Y. And so we have this here to get from here to here. Again, we're switching I and J, and we do that. That was a mistake on my part. This should be an epsilon. And then we get here. So to get from here to here, we're swapping L and K. That should, let's see, K and L. So I goes to L. I is going to L. Okay, so we're just renaming things, right? So I goes to L, L goes to K. Okay, so that's what we're doing right here. I goes to L, and L goes to K, and then that's just renaming dummy indices, and then we get this here, right? So, okay, so now we have this. The gauge transformation of the field strength tensor is therefore all of this, right? So we had this, we calculated this, and so now we have, so this guy here is this, which is what we calculated here. This guy here is this, which is what we calculated here, right? So now we divide and conquer. So we can take this guy here and this guy here and just do the integration separately. So when we do that, this guy here is this here, right? So all of this, right, so we're dealing with the red box right now. Right? So all of this is going to be all of this here. Right? So we're expanding this commutator over the indices. And then this guy here is just a covariant derivative. And then we take to go from here to here, right? So again, we're distributing. This is just distributing, right? So we distribute everything and we get this. So from here to here, let's see. We have C and C, C and C. This is A. So we can see the Kronecker delta is driving these C's to A's. Same thing here, Kronecker delta is going to drive that to a B. And then we have this guy here. This C is going to be driven to an A. And this C is going to be driven to a B. So we're getting rid of those Kronecker deltas. And then from here to here, we see that this term is, or this guy right here is right here. This one is right here. And these guys are all factors, right? So really what this is just factoring out things. Because this is right here. This is being multiplied by this one also, so it's right here. These two guys are the same, right? So A and B, B and A, but because these are scalar functions, these two guys are going to cancel out. What we're left with is this guy here. And so this guy here, we can actually, let's see here. So we take this guy, that's this. This guy right here is, oh, I see. Okay, let's see. So this is just product rule, right? The product rule. So this guy here is this and this one. So I can, so this here's this here, and then this here is this here. All right, so let's table that and let's look at this term now. So this term here is right here. And so we're going to use the Kronecker delta, right? So the Kronecker delta drives us to x. So we can take that out of the integral. We get this guy. And then from here to here, we have, we're going to drop the x just to condense a few things because these are functions of spacetime. And if you've been doing general relativity and quantum field theory for quite some time, typically that's what's done, right? You just drop the spacetime argument. And so, to just make things a little bit nicer looking. And so we get this. This here is this right here. Okay, we've calculated that before. This here is this right here. So if we can expand things out, right? Because this here, right, so let's actually do this, right? So this guy here is going to be right here, and this is multiplying this times this, which is right here, this times this, which is right here, this times this, we're going to get that g squared, and then this times this, we're going to get that g squared also, right? So, because this g is applied to here and we're multiplying by g there. So we get that g squared term. And then we can clean things up because we're using Kronecker deltas again to drive things, and Kronecker deltas again to drive indices to different names. Okay, as I've said, this video is going to be kind of long. Let's just continue to chug on through here. So now we can piece everything together. Right, so we get all of this. All right, so we switched signs, and we can cancel a few things. And so we get to this point. And so when we get to this point here, to get from here to here, we're just factoring this guy out, doing nothing here yet. To get from here to here, we, let's see, these two guys can be written in this way. We've shown that before. Right, we're relying on a lot of things that we've done before, right? Because we don't really want to go back and revisit all these mathematical tricks. And so we get this now and this when we multiply everything out. So a lot of things get ugly before they get nice, but we'll see how they get nice. So now we have this guy and this guy right here. So we can cancel things out again, right? Because we have NA, NB, NB, NA. And so we have an opposite sign here, so we can cancel those out. Again, these are those matrices that we were talking about, okay, earlier in this video. And so we have this now. All right, so to go from here to here, we have, we're really just factoring out this guy here, this lambda. And we're swapping names of indices also from N to L. Okay. So I'll just write that down also. So from N to L. And then from here to here, we're doing something similar now. We are factoring this guy out into more Kronecker deltas. And then these Kronecker deltas can be written in terms of epsilon tensors. So we're sort of doing the inverse now of what we've done up here. We went from epsilons to Kroneckers. Here we're going from Kroneckers to epsilons. But you'll see how this all collapses pretty quick here. Because now we can put this guy inside of this bracket term. Because now we have this here, this lambda L, and the lambda L right here now. All right, so this guy is right here. And then we, from here to here, well, this is just this guy, right? All this was just a definition of this thing, and we get this. Okay, so this guy in Poisson bracket with this guy is this guy right here. So, we now have proven that within the Yang-Mills framework, we lose gauge invariance in our electric and magnetic fields, right? The magnetic part being this one, and the electric part being this one. But here, so this almost seems to suggest that there's no physical observables associated with this theory. But there is, okay? And this is where holonomy comes back into play. Suppose we have a following mathematical object, which looks like this. Now this looks like it kind of comes out of the blue, but really this is just a path integral over a closed loop. This is a closed loop, this is the path integral. Alright, so it's a path integral over some closed loop. This, as you might recall, is a holonomy. Holonomy is the difference between the vector potential, which is important. Vector potential, it has to be a potential vector, before and after transporting it around a closed loop gamma. Before, or more generally, the holonomy is the transportation of a connection around a closed loop. So our holonomy is this guy right here. This is our gate. This is our potential, and this is our closed loop. And so, as we take our potential and move it around a closed loop, the potential could change, and the difference between the initial potential and the final potential around that closed loop is going to be given to us by our holonomy. So to make more sense of this holonomy, we can recall that emerge as a solution to our geodesic equations, right? So our geodesic equation was this thing right here, and if we multiply it by this, it should still come out to 0. But now we've put ourselves in a position now where we can actually define this object in here, which is exactly a solution to this equation. You can check the solution if you wanted to, with this being x, right, not chi. But this thing is it can be thought of as a solution to a geodesic equation. So this is some weird path integral over a closed loop over some closed loop can be thought of as a solution. This almost looks like a path ordering formulation of general relativity, which is quite interesting, with the holonomy being the action equivalent in this framework. So we can think of the holonomy as being the action that drives potentials along some closed loop, perhaps. So let's show that the trace of this quantity is invariant along any closed loop. All right, so to do that, we're going to do the same thing here. We're gauge transforming our holonomy, the trace of our holonomy. And when we do that, we get this right here, right? Because our holonomy is a function of our potential, and it can also be a function of our canonical momenta. And so, however, no, it's actually just if we say it's just a function of our potential, we can get rid of this term. All right. Now we plug this guy, the definition of our holonomy into here, and when so this is the definition of our holonomy. When n equals 1, we get our gauge transformation is this guy, right? So that comes from the fact when we defined, if we go, let's see, gauge transformation is right here. Whoops, went too far. So this really is just like this is our gauge transformation of gamma, and this additional part here comes from setting n equal to 1, and I don't think I actually put the equation into here when I should have. I think in the next video, I'll make the next video a little bit more elaborative on this term here. But let's just take this for what it is right now, because later we will see that in the case of n equals 2, let's see here, I'm missing something. Okay, well, we'll take a look at this term later. So I'm sort of taking this for granted right now, and so I'll make a video on this guy for the next one. Let's just take it as sort of accepting for what it is for right now. What this is it's this calculation, right? It's the generator for our potential. So the generator for our potential is right here, and we got that to be covariant derivative of this guy. So it really is just a covariant derivative of this guy. And the reason we have this Lie algebra is because it makes it more general. And but we should probably derive this just to ensure that we know what we're talking about when it comes to this. And I just didn't derive it here because I think my reasoning was that this should be a review of Yang-Mills theory, and so I didn't want to go in too deep into that. But when we do this, we get this term here, right? So this gives us Kronecker deltas again, and then from here to here, so the argument on this guy is y again, and so we can really what's going on here, what we want to look at is this term right here. And when we see that this term is here, is this guy, what we're actually finding is that when we multiply this guy through here, we get that the trace of any commutator between two matrices is going to be 0. So the trace of any commutator between two matrices, that's this guy right here, okay? And so, because this guy, we said, could be represented as a matrix, and this guy also, and so, because this is our gauge transformation, and we said that the gauge transformation could also be represented as a matrix in RSU2, and so what we get is this guy right here. And from here to here, this is just, we could, in theory, again, just cancel those guys out, we get the same thing. And so when we do that, we get this term here. And when we take the trace of some integral over 1 d lambda, we just get 0. Okay, so this is invariant. This thing is invariant. We can do the same thing expanding for 2 points along a loop. So really, so this n here tells us when we're going along this loop how many stops we're taking. So if n equals 1, we're making one stop, right? So so this is our one stop, say, our 1 point along the loop. For n equals 2, we're going to have 2 points along the loop. So one here and one here maybe. Okay. And so in a similar way, we can do the same thing here, right? So we take these guys and we multiply everything out again, driving with Kronecker deltas, and then from Kronecker deltas we get this guy here, and then we multiply everything out. And when we multiply everything out, what ends up happening is that you get these terms here. These terms here are just going to cancel, right? Or they're not really going to cancel. They're going to go to 0 because of the argument we made over here. Okay. And so what we have, is this here, which is right here, and this here, which is right here. Okay, so now from here to here, we have that, again, we're just moving the derivative inside, and we're integrating over two time points. We're doing the same thing here as we did before. We see that this is going to go to 0, this is going to go to 0. So for our gauge transformation, again, of the trace of our holonomy when n equals 2 is 0 as well. This pattern continues, and we can see the holonomy is gauge invariant quantity in Yang-Mills theory. So holonomy seems to be a deeper concept than local invariance. As we know, gauge fields are used to retain local invariance. However, when we promote these gauge fields to SUN in Yang-Mills theory, we lose that local gauge symmetry. in our canonical variables, but gain a symmetry in our new object called the holonomy, which represents the change in the gauge field over a closed loop. So these loops are closely related to the loops for loop quantum gravity, which we will come back to talking about later. We're at a point now where we are really defined exactly what the loops are, and the loops they really are just the invariant quantities under a gauge transformation in quantum gravity. And I've concluded this fairly long video on Mills, right, and Yang, because these are the two sort of head honchos in the development of this theory. So with that being said, I hope you like this kind of content. I'm aware that this is a long video, but with that being said, I will see you guys in the next one. Make sure to hit that like and subscribe button and go onto my Patreon page if you want to support the channel, get notes, and all the rest. I'll see you guys in the next one. Bye.